more people are joining. But I think we can start with the introductions already. So good morning, everybody. We will give today a workshop about ex-ante lifecycle assessment of emerging technologies. It's the second workshop. The first one was about defining the functional units of low technology readiness level technologies. And today's workshop will be about scenario development. As I said, my name is Flora Siebler. I'm a postdoctoral researcher at Leiden University, and I'm currently working in a Horizon Fed Open 2020 project, which is called Progeny. And we will also introduce the project again and what we did in terms of scenario development in this field. And then I want to introduce Stefano, or he can do it himself. So please, Stefano.
Good morning, everybody. Thanks for joining us today. I'm Stefano Cucurac. I'm an associate professor in industrial ecology at Leiden University, CML, and also part of the Progeny project. Together with us, Bernard Stoibing, colleague of ours, not directly involved in Progeny, but he will support us in the workshop.
Yeah, maybe you can quickly introduce yourself, Bernard.
Yeah, hi, good morning, everyone. My name is Bernard Stoibing. I'm the assistant professor at CML with a focus on prospective LCA.
Good, thanks. Then I will share the slides. So, as I already said, today's topic will be scenario development, and that's also why Bernard is here. He will introduce future scenario methodology, and I will start with a short recap of the previous workshop. And then after the scenario methodology introduction and also showcasing a tool which is developed by Bernard, the activity browser, I will again explain what we have done in the Progeny project. This workshop is together organized with Wasabi Innovation and Indranil Sen. He will join us later. And yeah, this will be today's workshop agenda. As I said, I will start very shortly with the workshop, the first workshop on what we did in that, and then the future scenario methodology with a general introduction, and then stressing again the foreground and background scenarios that we also have to scale them. And then in the end, the introduction to the activity browser and how easily we can implement scenarios there. And then how I was approaching this in the Progeny project. So let's start with the recap. We introduced last time what lifecycle assessment is about. So the 4 phases, we have the goal and scope definition. Then we have the inventory analysis, which is the most time-consuming part. Here we have to scale up foreground and background. Then in the impact assessment, where we take a look at impact categories like climate change or human toxicity. And then the interpretation phase, we also said that it is an iterative process which is in need of maintenance. So there's a lot of back and forth, as the arrows already indicate. And we follow ISO standards for that as well. And it is a quantitative method. Then we introduced also what ex-ante life cycle assessment is about, or prospective life cycle assessment, that there the focus lays in the early stages of a technology. So it's not in the market yet. So it's not ex post life cycle assessment. So we are in the concept or experimental phase, for example, for ex-ante. And this is not a challenge per se, it's also an opportunity, because at the beginning we have the highest influence on our technology if we make our decisions in a more sustainable way. So this we call the Calendridge dilemma, and we see it as an opportunity, and that's why we have ex-ante life cycle assessment. Then we already said that we need scenarios to look into the future in a way. So the future is uncertain, and how can we tackle that? All these solutions which might happen in the future in terms of our technology. So what's possible? So we build scenarios for that, and that will be introduced by Bernard today, and it's also the topic of this workshop. Then we gave, or we dove a little bit deeper into the first phase of the life cycle assessment, the goal and scope definition, where we also defined a functional unit. It's very important because everything is calculated around this functional unit. So all the unit processes which we define in the inventory phase, how much they add or have an impact to the functional unit, we take a look at. So because from all these unit processes, we then can see what is the environmental impact of our device. So defining the functional unit is very important. And also it is quite complicated in the Progeny project, which is very, very early TRL, technology readiness level. Then we also said that the functional unit ideally should be defined in the use phase of a life cycle of a product or a service, which is not always possible, but it's advised also by the ISO standards, and also to have a complete assessment, possibly from cradle to cradle. And then we took a look into the Progeny project, where we assemble, for example, devices like a new way how we can build up semiconductors. I will get into the Progeny project at a later stage again. And we figured that at this early technology readiness level of this process or of this project, it is not possible to define the functional unit yet. So we have to define sub-functional units and look into other stages of the life cycle, which we can assess. And this will be presented at a later stage as well for the use of clean rooms, and that we tackle that with scenario methodologies. So in the last workshop, we were able to show or repeat what life cycle assessment is about, then the challenges and opportunities of ex-ante life cycle assessment, and then also the stressing the functional unit, how important it is for assessing the environmental impacts of emerging technologies, and that everything is calculated around that. So now I want to hand over to my colleague, Bernhard. And
before Bernhard takes over, just a note for those of you who are tuning in today. The first workshop is available on YouTube. You can watch it afterwards, and this will be also available. And also, you should have access to the chat. So if you have questions, feel free to ask them. I will be monitoring the chat. The floor is yours, Bernhard.
Okay, fantastic. Thanks for the very nice introduction, Flora. Also really interesting to hear more about the the Progeny project. I'll share my screen. Just a moment. Do you see my screen? Okay, now let me bring you guys back. Okay, perfect. Yeah, so I have the honor to talk here about a number of different pieces of work that we've done in the past years about on the topic of future scenarios, and also the implementation of the modeling support of scenarios in LCA software, the activity browser. This concerns, so I basically split my talk into 4 parts. One is simply an introduction on the relevance of scenario modeling for prospective LCA. The second one is on a new, I would say, methodology or approach that we developed for foreground scenario modeling. Then an update or an introduction to the generation of background scenarios. And finally, a showcasing basically of how foreground and background scenarios can be used in LCA software. So we live in a time of great changes. We have climate change, we have technological transitions of a very high magnitude. All of that needs to be environmentally well guided and supported. Otherwise, it's going to be difficult for us to meet climate targets and other environmental targets. Prospective LCA is one of the key means to that. Prospective LCA tries to anticipate environmental impacts of products and services by future technologies. So one thing that is really core to that is the assessment of scenarios. I think as Flora already highlighted, if we're here in time, we don't know what will happen here, but we can make up different scenarios and try to guide technology developers not to end up here, but rather to end up here. Let's make this a little bit more practical. So let's take a car manufacturer who wants to make an LCA for an electric vehicle in 2030. And a system that he might be looking at is something like this, where he's the EV producer, right? He buys steel and batteries maybe and produces an EV. That EV will be used. And throughout all life cycle stages, we have the consumption of energy. Now, a part of that system will be under the control, or at least in sort of the knowledge domain of the EV producer. And we call that the foreground system in this case. And then we have the much wider economic system that is basically beyond the control of the car manufacturer. So we take this as the background system here. So the car manufacturer will have developed 2 kinds of scenarios. He will have to develop foreground scenarios for how the EV will develop in 2030. And he will have to maybe not develop himself, but have some background scenarios or some ideas on how the economy in 2030 will look like. This is quite important, but it's also really difficult to do, at least for individual stakeholders. Now, a few things that the car manufacturer or the LCA practitioner should watch out for. One is that he should have narrative consistency. So if he develops a very optimistic scenario for the foreground system and a very pessimistic one for the background, that may not fit together. So something like this may be better. Maybe I should turn on the pointer. Can I do that somehow? I think that's actually nicer. Here we go. So narrative consistency is important to consider. Now it doesn't let me move the slides anymore. Here we go. The other issue to watch out is temporal consistency. So if the LCA is supposed to represent 2030, then both foreground and background system should represent 2030 and not one 2020 and the other 2030. If we don't do that, it's like placing windmills in an economy of that time. Thanks to my colleague Brenda for this great pictorial inspiration here. And does it matter for the LCA results? It matters a lot. So if you look at the EV example here, it's really not so much about this car here. It's about where the electricity comes from. So the background really matters. And the slide is also to highlight a little bit that we need to be careful to get these LCAs right, because LCAs are influential in shaping public opinion. And if we publish a study like this, EVs are dirty because they're based on coal power, right? We may actually, I mean, this has hopefully nothing to do with the future. In the future, we're going to be closer to a system like that. And then there is some potential. So I think our task is really to try and look into the future and see what has potential rather than scaring people away from novel technologies just because right now they're not optimized yet. Yeah, and then a final slide that things are always a bit more complex. So LCA practitioners have been traditionally good at modeling future scenarios for the foreground and have always struggled to take the background into account. And I'll give an example here now how different parts of the background system are more easy or more difficult to take into account. So it's fairly straightforward for an LCA practitioner to alter the electricity mix that is directly used in the EV, for example, here, and thereby simulate a future scenario. He can still also take that into account for production. But the more actually we look at a full integration of these future technologies within the supply chains of the EV, the more difficult it becomes. For example, there's also simply loops between the electricity mix and the impacts of electricity generation. You can think about PV panels. If they're produced from our current mix, they still have a considerable upfront carbon footprint. But if they're in the future produced from cleaner energy, then also their carbon footprint gets smaller. And because it gets quite tricky here to take this into consideration for regular LCA practitioners, here's the legend. I think it's really important that we as a community have future background systems available to help us to take really the full integration of future technologies with future economies into account. Okay, and with that, I don't know if we have a question stop. What did we plan, or should I just go ahead?
Yeah, you can go ahead, Bernard, and then we'll pause in a moment for questions after this block on foreground scenario modeling.
Perfect. Okay. All right. Now I'll talk about the methodology that we developed for foreground scenario modeling. Here's some starting points. Very important for us, a paper by Spielmann, a methodology to generate scenarios for prospective LCA based on formative scenario analysis. That's a good method, although perhaps, yeah, it needed some improvements, and we tried to simplify a few things in our approach. Also highly recommended a literature review on scenario approaches in LCA by Valentina Bisinella. Yeah, this is the approach that we're developing right now. I'll dive more into this now. We have a paper in preparation, but it's not published yet. Okay, so the approach consists of basically marrying or integrating a scenario approach and life cycle assessment. And we did that for the first two phases of LCA, so for goal and scope and for inventory analysis. We present a practical, iterative, and stepwise approach. And for each step, there are specific tools to be used and recommendations given on other tools available as well. And this methodology has been tested in a number of case studies, as you can see down here. Now, what does it do? It's fairly simple on the goal and scope because it's not it's supplementary to the steps that you're doing in goal and scope. So it's not a comprehensive repetition of all the steps in goal and scope, but certain points of attention. The first one is the scenario type. Is the study predictive, explorative, or normative? Predictive is basically a study trying to assess how the future will be. Explorative is how the future could be, and normative is how the future should be. Then the time horizon needs to be defined, also the reference year of the technology. So when will it be on the market, for example? That is often the point in time for which the LCA will be made. And also the technology readiness level at the current state and at the state of the assessment in the future. And then, of course, initial choices regarding foreground and background data, as well as the identification of alternatives, so which systems should actually be included in the comparison. In the inventory analysis, that's the main, I would say, contribution of our approach. We identify 4 steps. The first one is the identification of influencing parameters. The second one is the construction of sub-scenarios for each of these parameters. The third one is then the and sub-scenarios means specific values that each parameter can take, just thinking independently for each parameter. And then in C, it's sort of the integration of these parameter sub-scenarios of the possible values of parameters into scenarios where they make sense together. And the final step is the implementation of the scenarios in the inventory model. And I'll go a little bit more into depth now. So during the first step, we can perform a pestle analysis, and a pestle analysis is basically nothing but a structured brainstorming. You can see it as a table where you can fill in now what comes to your mind in these different dimensions here: political, economic, sociological, technological, environmental, and legal. It's good practice, of course, to do that with the stakeholders involved. So you can really start by simply mapping all of the parameters that could have an influence on the technology in the future. Then in the next step, we recommend to draw a causal loop diagram, and actually even to combine a causal loop diagram with a flowchart or a flow diagram. And this is what we try to do here. And I'll, for an example of a biopolymer case study, and I'll try and explain the reasoning behind this a little bit now. So the LCI model is, of course, the technical or the LCA representation of the technology in terms of processes and flows. And it's always sort of that's the ground truth, or the how do I say, well, that's how the technology is ultimately represented in the LCA. So this needs to be very clear to the practitioner what he can do at this level. So this is something to consider. But then on the other hand, we have parameters maybe influencing specific aspects of these processes. We call them technology parameters. And then if we think even more in the bigger picture, we also have surrounding parameters. So all of the social, economic, and political aspects that influence the conditions for the technology in general. So we could also take a walk from left to right here. We could say that the production scale, for example, depends on the demand for biopolymer, and at the same time on the biomass supply. And then depending on how the production scale is, whether it's high or low, that will influence the average transport distance of biomass. It could influence the yield of the technologies. It could influence whether certain components of a technology are installed or not, like acid recovery, how much electricity is used, etc. And then you can also see that we have two shades of blue. We also have a darker blue, and that is already in sort of in view of the thinking that we may have also background scenarios available. So certain factors like the share of renewables may be modeled via background scenarios. So we could also say environmental policy perhaps influences the share of renewables, and that will affect how the market for electricity will look like. So this is an iterative process, and it often starts out in a very complex way, and then over the iterations this should get simpler as one eliminates parameters that are maybe not of such great importance. In the next step, it's about thinking about the possible sub-scenarios or the values that each parameter can take. So if we have a list of parameters here, environmental policy could be liberal or strict. The share of renewables could be low or high. The production scale could be small, medium, or large. And the acid usage could be low or high, for example. Or if it can be quantified already at this level, then you can simply put the numbers there. So this is step B, thinking about possible values for each parameter. Now, we've heard about ex ante LCA and from also prospective LCA that there is this immense challenge of coming from or thinking when you're in a state, in an early design stage here, how such a more mature state will look like. And it's certainly going to be quite different. There's going to be different technology, different kinds of processes, different inputs. There could be different, certainly, hopefully, efficiency increases, energy integration, and so on. So there may be, depending on your technology and the development on the technology readiness level scale, it may be necessary to do upscaling and further data estimation, but this is not part of my talk now. The next step, once we have all of the scenario, sub-scenario values for each parameter, we can think about the creation of scenarios. And there may be a couple of tools that can help. One is a consistency check. So especially if there's many parameters, then there's also many possible combinations of specific values for these parameters, and you may get into hundreds, thousands of scenarios in if you just do the combinatorial thing. But some of these sub-scenarios will not logically fit together, and this is the purpose of the consistency check, to identify which combinations are consistent or rather not consistent. So here, for example, we have asset usage versus production scale. So it's always a pairwise comparison of the parameters. And then for the sub scenarios for these parameters, we see that a high asset usage is incompatible with a small production scale. And we can see that here a large production scale is compatible or consistent with a high asset usage. And in between, there are some possibilities, and these are rather no-goes. So these scenarios here would fall out, and that would reduce the dimension space. This can be done very nicely also in parallel with morphological fields from general morphological analysis. For example, we can simply write out all parameters and their potential values in a table like this. And then we can say, well, if we predefine, if we assume that we have a small production scale, so red means this is what we have defined, then we get these possibilities. So blue are the possibilities, and we can read these possibilities out of this consistency analysis. So we see if we just define small production scale, we have quite a few possibilities left still. So maybe we need to think further and say, well, if we have small production scale and a liberal environmental policy, and then now there is only basically one consistent solution to that. And this is a way of perhaps deriving scenarios. And of course, this is always, well, it doesn't have to be these tools, but they can be helpful. This is quite an iterative process, simply thinking about what are potential narrative, what are potential scenarios, and of course that should also be discussed with the stakeholders. Now that we have developed scenarios, we can basically state them like this. So we have the different parameters and their different sub-scenarios, and now we can express the scenarios like this. So we have, for example, a worst case narrative X and best case scenario, and they take different parameter values for each parameter. And having done this, we're almost on the way to implementing that in LCA software. At some point, we need to quantify all of the parameters that we include in the LCI model. So we could also, instead of writing small, medium, large, we could already write the values here. That would also be a possibility. At the latest here, when we pass on this data to the software, it has to be quantified. And I'll show later today an example of how this file format could look like. And of course, we can use background scenarios if available to complement the scenario analysis and choose consistent background scenarios with the foreground scenarios. Okay, takeaways from the scenario modeling. Designing good scenarios is really important for providing environmental guidance based on prospective LCA. The identification of parameters that could play a role in the future is an important step. So the exercise itself, the scenario development, brings in value beyond the results, but teaching the LCA practitioner and the stakeholders more about the interrelations of their specific system with other systems. So there may be a lot of learning involved. There are many ways, of course, in which scenarios can be developed. That the reason why we developed this methodology in the first place is that often in LCA literature, it's very opaque how scenarios have been developed, and it's not very well described. In a way, we're missing a good standard procedure for that. So this was our idea to present a simple and structured approach to document and transparently report on the scenario development. Yeah, and the work has been funded by 2 different projects, and there will be a scientific paper soon, and also a JRC report covering the same. So I think I can take questions at this point.
Yeah, let's see. Feel free. Thanks a lot, Bernard. I think already interesting for now. Looking forward to the next bit on the background as well, and then to the software demonstration. To all participants, feel free to use the chat to ask any question before we move on to the next bit. I don't see any question yet.
If not, we can also bundle them for the end, maybe.
Of course, yeah. And if in between there are other questions coming up, just put them in the chat and we will collect them back later. I see someone typing. Maybe we give it 2 seconds, Bernard. Oh, all clear so far, so we can move on.
That's also good feedback. Thank you. All right, then we move on. Yep, okay. All right, then I'll talk about background scenarios and their generation. So first of all, I personally like to use, I've been pivoting between different terms, and for people who know my superstructure approach paper, I've used scenario LCI databases, but I'm now pivoting to this term PLCI database as opposed to just LCI database. So it's a prospective lifecycle inventory database, basically representing a specific future scenario at a specific future time, but it's a normal LCI database, simply with different values. All right, so how have these PLCI, prospective lifecycle inventory databases, been generated? Maybe a short history about them. In 2004, there was the NEEDS project, and that was actually the first systematic approach to generate future scenarios of the EcoInvent database. They futurized electricity supply and other sectors. Then another big milestone was in 2015 by Ante. They modeled the Themis model, which is a hybrid multi-regional input-output and LCA model that includes IEA energy scenarios and the needs scenarios. So these are important milestones. Another big milestone was the study When Background Matters from Mendoza in 2018. And that, for the first time, coupled an integrated assessment model, the image model, with the EcoInvent database, also for electricity supply. And the interesting aspect here is that the IAMs model different SSPs, shared socioeconomic pathways, and RCPs, representative concentration pathways. So these are the SSPs are sort of big storylines about how the future will or could develop. And RCPs are possible pathways for emissions as modeled by the IPCC. And the nice thing about using IAMs in conjunction with LCA is that in a way we save some of the hard work of making scenarios, because we're hooking on to already widely accepted storylines from other disciplines. Another milestone was the premise framework by Romain Saki in, well, basically now. It already started during this work and was then refined into a Python library that is publicly available for generating prospective LCI databases based on by now different IAMs and including beyond electricity also additional sectors. So how does that work? How to generate, share, and use prospective LCI databases? Well, first of all, there's what I call the IAM approach. So we take an IAM, which is based on lots of other data and these SSPs and RCPs, and we couple that data, or we use that data to futurize an LCI database via so-called integration software, such as Premise. And the result of that is different prospective databases representing different scenarios at different points in the future. These can then be imported in LCA software and used by LCA practitioners to derive decision support. And the second approach is sort of the custom approach, which is very similar to the previous, the IAM approach. It's only differing in this box, which is basically that any scenario model and data can be taken to futurize an LCI database, and then we can produce future scenario databases. Of course, we don't want to sort of miss out on this work. Well, maybe first of all, why would we do that? We would like, or we'd be interested in doing that in cases where the IAMs don't have sufficiently good data on a specific sector or geography or technology. So IAMs are great data sources. They claim to have a certain level of consistency, but they're also broad and aggregated in many respects. So in some cases, for example, here in these studies by Habrecht and Meide, we looked at specific metal supply chains, and such data. We actually used some IAM data in there, but we also used lots of other data to make these scenarios with the intention to make the scenarios as good as possible. Of course, we don't want to miss out on what has already been developed here from the IAMs. So when using custom data, it should be sort of best practice to still align with the overall storylines of the SSPs, for example, and to see how this can be developed in the best way so that it fits with, for example, future electricity backgrounds that are available already. Does it matter in terms of LCA results? Yes, it can matter a lot. So here we see the results from Angelica Mendoza in 2018 for an EV, climate change results, and depending on different scenarios until 2050, the carbon intensity could be either the same or be reduced by 75% just by greening the electricity supply. background scenarios matter a lot. We see that also for the climate change results of different metals. This is a result from Carina Harprecht, where we see that over the next 20, 30 years, the impacts from the for metals are mostly declining for most metals, and it really depends on which metal, whether that effect is large or small. But for example, good news here is that for copper, it could be as large as a 70% reduction. And yeah, we observed for almost all prospective LCA studies that we perform that the background can really have a very strong influence. Some of the challenges for prospective LCI databases. One is sectoral coverage. We still need to increase that. Second one is environmental coverage. The focus so far has been mainly on climate change. We're not that good yet at modeling other or including data for other environmental dimensions. Sometimes we have this trade-off between consistency and quality, and this is what I just tried to highlight already a bit with the custom scenarios versus the IAM-based scenarios. If we look at specific sectors, then we often want to deviate a little bit from the data sources to increase the quality, but then we're hitting a little bit maybe the consistency of the data. So this is something, an ongoing fight between these two ends. Harmonization and acceptance is another construction site. So in the future, we don't want to have a million different scenarios. It would be much better for the community to have good scenarios, but few scenarios actually, so that our studies remain comparable. We need to figure out better ways of sharing these background scenarios or PLCI databases. And we also need, except for the activity browser, I think the support for using such background scenarios is rather limited in other LCA software. So takeaways here, good scenarios really matter. Again, same conclusion here, scenario modeling is really important for the LCA results. And also for stakeholder opinions and actual decision making. There is some hope because we increasingly see prospective LCI databases being generated with increasing quality and coverage. So this is quite exciting. And we see a lot of people starting to use these databases, at least in the scientific domain. But we also have these hurdles that I mentioned to be taken before this can become more mainstream. Okay, I think I'll just continue, right? Unless there's questions at this point.
Yeah, we can we can leave a minute for people to type questions, for participants to type questions in the chat. Thanks, Bernard, also for the historical overview and the evolution of the concept. Also very interesting, and for translating the complexity into understandable words and to a clear flow. And I very much agree with your takeaways on scenarios and on the necessity to harmonize things as well, going towards making these mainstream. All right, I see multiple people typing, so maybe it's a good moment to take questions. You said more or less in every context, the background scenario is quite influential, as we would expect. Have you also studied how much of this lowering of impacts is due to the decarbonizations and how much to other factors like improved efficiency, change in technologies? Giuseppe Cardellini is asking, Bernard.
In general, I can't give an answer to that, but in the studies that I mentioned here, we did, of course, that. So for the copper example, I know that a lot of it has to do simply with a shift from one technology to another. For the electricity declines here, that's the penetration of renewables, and the also the efficiency increases made during the production of electricity. And there's, of course, if we combine them, there's sort of co-benefits, right? So more deeper integration, so more renewable electricity affecting the supply chains of metals, and then thus cleaner metals for more renewables. This is a, how do we call it, a positive feedback loop or something like that. So it's mutually beneficial, these effects.
All right. We have a question on the IAM models, which make predictions up to 2100. And LCA results showed indeed significant differences when applying them, but much less for a time horizon at 10, 15 years. So would you recommend to apply such PLCI depending on the chosen time horizon, Bernard? Laurie is asking.
Yeah, we typically just, I mean, of course, yeah, IAMs go until 2100 and partly beyond. I have no idea how the future world will look like in 2100. And we always felt like we probably, we didn't dare to go further than 2050, 2060. That seems far enough. But technically, yes, you can have prospective LCI databases based on IAMs until 2100. There's no issue with that.
And did you also notice this impact on this 10, 15 years time horizon?
That there's not such a big difference in the next. I think you can see it in this curve here maybe already. I think that's probably also a matter of how we think about the future and how we can imagine, you know, big changes in the next 5 years. No, we cannot imagine that, but maybe, yeah, in 15 years, that's far enough away that, you know, scenario modelers, also the IAM people, they need to make choices, right? It's always easy for politicians to commit to big changes after their term, and especially for 2050, it's easy to write down goals.
Yeah, no, very, very good point. There's a question about the accuracy of scenarios and whether anyone has checked whether scenarios in general, perhaps also the scenarios used by IAMs, have proven to be accurate in the past. I think there's broad discussions in the sustainability disciplines at large related to how accurate scenarios are in the first place. But maybe let's hear your take on that, Bernard.
Yeah, a purely personal take. No scientific objectivity to that at all. All of these scenarios are not perfect. That is the simple bottom line. And I think if you look at the IEA scenarios for the development of the renewables, they have been consistently too pessimistic. And I wouldn't be surprised, or my secret hope is that this is also the case for all of these scenarios here, that we're still not creative enough in our minds to really realize what kind of quick changes we could have in the next decades. So these could be underestimations, but I don't know. We don't know. And I think it's still better to take these scenarios than to just stick with, you know, non-futurized LCI databases as backgrounds.
Yeah, very good point. I think we can move on to your software demonstration, Bernard. If there are any questions, feel free to put them in the chat and we'll try to answer them at the end of your presentation.
Okay. Great, then I will try to show now how to do some very simple foreground scenario modeling, how to include background scenarios, and how to combine foreground and background scenarios in the activity browser. And then I'll quickly introduce the superstructure approach and do a recap on the on this last part. All right, let's start with a very basic EV model. So we have our EV here. It requires electricity. It requires the car itself and the battery. This is our simple model. And here we just connect to upstream supply chains from the eConvent database. Now, let's implement a foreground scenario or foreground scenarios on the electricity, passenger car, input and battery. And let's develop a lightweighting scenario. So this is, of course, not realistic at all. It's just completely made up for the purpose of illustration here. I assume that lightweighting will lead to requiring less of the passenger car, less electricity, and less of the battery. That is the simple foreground scenario developed here, and less means we reduce each by 1/3. So this can be modeled in a number of ways. All of you know probably from your LCA software that you can either directly change those values in this process, or you could make a copy of that process with the changed values. Some of you will also know that you can perhaps parameterize a process like this and model the change like that, and use different values for the parameters. This is what I call parameter scenarios. Then I would also like to show you another concept, which is basically boiling down to changing the values in this process. I call that flow scenarios, making use of a file that we call a scenario difference file. That's a simple Excel file which identifies these three inputs to this process and can record as many other values for these three flows as you like. So that's simply instead of doing this within your LCA software or copying processes, the last option simply outsources that to Excel. You can load that file and you can change these three inputs as many times as you want. Let's look at how this works in the activity browser. So I bring it up here. I'm not sure it's really full screen. Can you see it well? Yeah, okay. I don't know why it doesn't go here, but it's fine. So here we have a database in the activity browser. I'm sorry for those people who are not familiar with the activity browser. There's also YouTube videos on the installation and on the sort of how to use the activity browser in normal ways, but I don't have time to introduce that now. So here we have three activities. We have the EV with providing 1 kilometer of driving, everything very simplified here. It uses 0.18 kilowatt hours of electricity, this amount of the car, and this 3 grams of lithium ion battery for driving 1 kilometer. Now the approach of simply copying and making these numbers more efficient, if you look at this part here, is represented by this copy of the process. So we have simply reduced these numbers now by 1/3. And the other alternative way of modeling this we discussed was the parameterization. So now you see we have different values here. That is resulting from multiplying the original values by an efficiency factor. And this efficiency factor is set to 0.67. So that's roughly the 1/3 reduction. Now, if we calculate an LCA for that, so if we have these three processes and I calculate an LCA for climate change, then we get these results. So this is the original driving process. This is the more efficient copy. And this is the parameterized data set. You see it leads to the same results, doing it in different ways, but same results. And now I'd like to show you that you can also just work with either parameter scenarios or flow scenarios. So you can switch here to scenario LCA, and you can import let's start with the parameter scenarios, and I'll just show you actually quickly what is in that file, just so you understand what we're talking about here. So parameter scenarios is basically as easy as this. You remember that we had a parameter called efficiency factor, and now I included two. You can ignore these two columns for now. Now we have two additional scenarios. One that is more efficient. So this is our sort of improved scenario, and then one that is even better, right? 50% reduction through light weighting. Let me just move that. Okay, so let's do the LCA for that. So these parameter scenarios simply allow us to, instead of changing the value of the efficiency factor, we can change that in an Excel spreadsheet, and we can of course change as many parameters at the same time as we like. So we can add additional rows and construct real bigger scenarios from that. You can see now no change across the three scenarios for the first process and for the copy of the process. That's as expected, right? Because we didn't parameterize them. And we see that here there is a change in the parameterized model. And that is due to the fact that actually default just takes the value that we gave already here. So this is this value overrides it. So we have two scenarios for 1/3 reduction, which is what we see here. And we have one scenario for a 50% reduction, which is what we see here. Now we can do the same also by, sorry, let me go back, by modifying the flows of this process via flow scenarios. So I load another scenario file and I load the flow scenarios, and I'll just show that to you, how that looks like. So the flow scenarios, it's a little bit a more complicated looking file, but it actually isn't very complicated. All of this information is simply for identifying the exchange in the LCI database. So this is the from and the to part, or if we go back to our slide here, it's basically, so this would be the from and this would be the to, and this is the from and this to, etc. So it's about identifying these three exchanges here. This is what we do in these columns, and the AB can help with that. And then we identify, or we define, additional scenarios. So we have a default. With the default values, we have a improved and an even better scenario. So let's see what that does. If we find, here we go, calculate. So here we see no changes in these processes because we didn't, our scenarios don't affect them. They only affect the first process. And we see the three scenarios reflected as expected. Okay, so this is these are possibilities of implementing scenarios. I personally would do it in the third way, the flow scenarios, because that is the most flexible and also the most robust, and it combines quite well with background scenarios. Now let's move on. So this is what we've seen. Let's now talk about background scenarios. So now we'd like to also have a scenario for how this electricity is supplied. And here we take a futurized version of the eConvent database based on the image model for the SSP2 and RCP 2.6 scenario. How do we do that? Let's go back to the AB. So here you notice now actually if I look into the activities, you actually see that the electricity input, all of these inputs are not coming directly from the eConvent database, but they actually come from a database that already represents a superstructure for the eConvent image combination that I just mentioned, and I'll talk about that in a moment. But this makes it very easy now for me to load scenarios for this background database, and I'll do that now. So I'll add the superstructure, the scenario difference file for the eConvent 371 image combination. This is a much bigger file. This is why it also takes probably a minute or so to load that, and I'll give you a bit the reason. You can see it's actually the same structure as the flow scenarios that we just looked at. So it also has this from part and then the to part. So what we're doing here is, again, identifying exchanges in this superstructure database. And then we have three columns for different scenarios. So we're going to look at 2020, 2030, and 2050. And you can see this is not just changing three exchanges. This is also why it's so difficult for individual LCA practitioners to really develop good background scenarios. Here we're actually modifying 217,000 values or exchanges in the futurized eConvent database for each scenario. Okay, let's see if now it loaded. So we can see now we have these image SSP2, RCP 2.6 scenarios for the 3 years. And if we now calculate that, so it will basically replace in that background database these 200,000 values for each LCA calculation, so that we really have a different background database or different background scenarios as a basis for the LCA. And here you can see the results. You see that in our driving inventory, the background really matters a lot, especially the step as one of our colleagues questions mentioned before, especially the step now after 10 or 15 years matters. And it affects now every so all three processes, because all three processes build up on this background system. Okay. Now, can we actually also combine now foreground and background scenarios? Yes, we can. So we can do that by simply adding another scenario file. I get the second load option here. And if we now include also the foreground flow scenarios, and so now we have a combination actually of these scenarios. So we'll get not 3 but 9. We'll get for every 2020 scenario, we'll get for the 2020 we get 3. All of these assessed for 2030, all of these and for 2050. And you see it here now. Well, first of all, the flow scenarios, you remember they don't affect these two processes. So the changes here are purely background scenario driven, as before, basically in the last LCA we did here. But you see for the foreground, and now unfortunately the legend is blocking that a bit sometimes if I move this around, or sometimes the legend moves. Oh yeah, it moved. Nice. Okay. You can see that so the first 3 are always 2020, 2030, 2050. So here you see that for 2020, it still matters a lot how efficient our EV is, and the same goes for 2030 and even for 2050. Yeah, obviously, if we consumes half the inputs, it will still have half the impact even in 2050. So this is the combined optimal result in the future lightweighting and renewable energy. Okay, great. Do we still have time, or shall we rather wrap up?
Yeah, I think in the interest of time, it would be good to wrap up. Bernard, maybe just a few words about where to find the right information on the superstructure approach, and
Great.
then just to give enough time to show another practical example within Progenio of the use of scenarios after that.
Great. Okay, I'll keep it very short here on this last slide. This is basically the theory behind how this works, that we can futurize background systems and then combine all of these possible scenarios basically in, well, one of the practical modeling challenges is that in theory we would get a single prospective LCI database for each scenario and time step, and that is very unpractical to model within LCA software. And this is why we came up with the superstructure approach, which basically compresses all of these databases into one that you can work with. Like we've done now, our foreground system linked to a single database that we were able to turn into different future backgrounds using the scenario difference file and the superstructure approach. And you can read more about this in this paper here. Okay, I don't know how much we actually need to recap. Yeah, I basically showed different ways of implementing scenarios, from a simple copying and modification of data over parameterization, over more sophisticated scenarios at the exchange level, to in the end a combination of background and foreground scenarios. And I wanted to highlight this, although I was talking about options implemented in the activity browser here. I think the ideas are generic and the implementations are partly available, I think, also in other LCA software, or could, and this is what I really hope, could also be implemented in the future to make scenario modeling much easier. I think that would be really helpful. Okay, thank you very much, and I'm happy to take questions if we have time left.
This is a very excellent excellent overview, and also kudos for your live demonstration, was flawless, so perfect there as well. And I'm happy that we have this on record for future reference as well, to share with students and practitioners as well, beyond Progeny, I mean. Any questions to the point specific to Bernard that from anyone in the audience? I don't see anyone typing. One question coming up. In the meantime, maybe Flora, you could get ready for the last bit of the presentation, I think.
Yes. Bernard, could you stop sharing? That would be great.
Sure.
And thanks for the presentation. I always learn something new. That's amazing. And I'm a big fan of the activity browser.
Happy to hear that.
One last question, I think, Bernard, did you investigate the uncertainties of defining the scenario values, or attributing uncertainties on the scenario more or less probable?
Yeah, my personal take so far on this has been that these scenarios are already so uncertain themselves, or they're sort of the breadth of the different scenarios is kind of capturing some of the uncertainty, and would be very difficult to put uncertainty values on. I mean, in theory, it's possible to put also uncertainties onto the values in the future scenarios, but nobody has done that so far.
Yeah, I think we played a bit with the idea of even randomizing the selection of scenarios and scenario parameters at some point in a sort of Monte Carlo simulation that also plays around with probability or possibility of scenario, or one scenario being more probable than the other. But for now, it's just exploratory research. And I agree with Bernard that it's possible. But probably is not necessarily useful at this stage, given the uncertainties are already embedded into the scenarios themselves.
Although it could be quite interesting for certain foreground systems, where technology developers actually know something about the inherent uncertainties of technologies even in the future. Then I think it could be interesting.
Yeah. To be continued.
Definitely.
Yeah, thanks a lot, Bernard, and
yeah,
thanks for being with us today.
Thank you.
Yeah, sorry. Then I will take over, and yeah, we heard now a lot about the future scenario methodology, and in the Progeny project, I picked partially this scenario methodology up, but I changed a bit the viewpoint. But before we get there, I want to introduce again the Progeny project. Here you can see a very nice soap bubble. It looks a little bit like a picture from the sky taken of the Earth. Yeah, and Progeny is basically about soap. And it is one of these disruptive technologies which will be developed in this project, because this soap, which is designed within this project, the designer soap or poems, they are called, they have different kinds of properties. So they have protonic properties. They could be used for prosthetics, interacting with prosthetics. They have optical properties, as you can see on the right side, even used as a screen. They have electronical properties. So one of the goal of this project is to build a new kind of semiconductor, which is embedded in almost any kind of technology. And it has also acoustic properties. That's also where the name is coming from proto-optoelectronic mechanical hybrid systems for next generation bionic devices. So very hard to explain in only a few words, but you might maybe grasp this complex project and that it might be one of these disruptive technologies for the future, because it is based on surfactants which make up soap in a way. They are designed that they can have electronical and optical and so on properties. And yeah, it is a Horizon 2020 FED Open project, and we are in the first year or the second year now of this project, very early stage. We have technology readiness level of 1 to maybe 3, depending on which part you're looking at, which makes it also quite complex to investigate. And in the last workshop, we already figured out in a way that defining a functional unit to calculate the environmental impacts around is quite difficult. So we have to take a deeper look into the unit processes making up this technology, this device. And one of these unit processes which we probably will need is the usage of a clean room, so a defined space where the device can be assembled, so free from dust and any kind of particles. But we do not know which kind of ISO standard of a clean room we need. So is it ISO standard 1, which is super strict and very, very clean, or is it maybe ISO standard 6 or something in between? So the motivation to investigate this clean room usage in progeny was to find a multifunctional solution. So we allow a lot of different kinds of scenarios to express a clean room. And yeah, since this is in a very low tier technology readiness level, this project, we also have to think about projecting it into the future. But that's not the only motivation for this research we did. We also want to help the life cycle assessment community in building up this background data for clean room usage, because not only progeny devices are in need of a clean room, any kind of technical device will pass through a clean room at a certain state of their life cycle. So semiconductors, photovoltaic cells, almost any kind of technology has to be assembled in a very clean environment. Then we also wanted to take a look into the question if the location might maybe matter for clean rooms. So do we want to have clean rooms built in the future more in Europe or maybe in Southeast Asia? So we were taking a look into that as well. And then also we wanted to test this theory, if it's possible to use life cycle assessment as sort of impact screening method to reduce big solution spaces in a way that we can already exclude very dirty solutions in a way. But I will come to that in a second. So why is a clean room or this defined clean space so energy intensive? Already in the 90s, researchers found that this is just for general buildings, so not clean rooms per se, that the energy is a big contributor to the sustainability of buildings. And the greenhouse gas emissions, they come mainly from the air handling unit or also heating or cooling this environment, this place. And clean room has air handling unit for that to clean this space. And it consists of a recirculation air unit and total makeup air unit, which also takes care of the in and outflows with the environment. So if we're in a climate which is more tropical, or if it's more cold climate or temperate climate. So the heating and cooling part. So what is a clean room? According to the Oxford Dictionary, a clean room is an environment free from dust and other contaminants, used chiefly for the manufacture of electronic components. And as I already mentioned, there are ISO standards to define these clean rooms, and basically they just say what kind or how many particles in which size are allowed. So ISO class 1 for a clean room would be very clean, a very strict environment, and ISO 9 is like a defined office space. ISO 5, for example, would be necessary for manufacturing semiconductors. So with the help of the general morphology analysis, which we heard of before by Bernhard, we identified different morphospaces and all kinds of parameters which have an effect on this defined space and the particles amount, the particle amounts. So we have in gray the technical morphospace, and in yellow the environmental morphospace, so like location and how many airborne particulates are there. Then we have also an economical morphospace where energy costs or labor costs are included, and they all have an effect. But which of these parameters actually can be quantified or contribute to the life cycle inventory of LCA? For integrating a clean room in life cycle assessment, we of course need the clean room classification. Is it ISO 1 or is it ISO 5? Then we need the equipment, which is basically the area which is needed to assemble the device. So how much area of a clean room is needed. And then the energy density of a clean room. So how much energy do we need to maintain this clean area? And then, of course, the throughput of the device, how many of the devices can be assembled in a certain time. And yeah, here are just some of the connections to the other morphospaces. And we let the functional unit be very loose. So we allowed all the ISO classes of the clean room. Yeah, and so on. So in the end, we had a big solution space, which was made up by 4 parameters with a lot of variations, like the ISO standards, 9 different ISO standards. We allowed then, we also included the technology efficiency increase, that in the future, for example, the efficiency will be increasing of the clean room usage, or by turning, for example, the operation conditions off during the night. Then we also were looking into the future, so 9 different future projections, and then also spatial resolution to include the climate. And in the end, we had 68 trillion different impact indicator results. And yeah, we could show them also on 240 different impact indicator maps. I will just be a bit quicker here because of the time. To project everything into the future, we try to be as consistent as possible. We used Köppen-Geiger climate data. Then from WorldClim, we were able to get temperature data from which we could derive the energy demand for heating and cooling. And then we used the superstructure for the impact of the energy mixes. Here is the resolution of the temporal resolution of the background data we used. And then the spatial resolution was also a little bit different. So Köppen-Geiger climate data is 1 kilometer. Then the temperature was 10 minutes. And then the impact energy from image is in regions, 26 different regions. So how does the results in the end look like? So this is one of the impact indicator maps for the year 2030 and ISO standard, clean room ISO standard of 5. on country resolution, aggregated. This would be the same for all ISO 5 scenarios, clean room ISO 5, on region resolution, so the energy mix regions for the different future scenarios. But now we have all these solutions, and what does impact screening mean in that context? We apply, for example, a threshold where we say this is a too dirty solution for us. So for example, like this threshold, then we can already exclude some areas, and we can also zoom in some areas. And then we have the spatial resolution and can say, for example, okay, if you want to build a clean room in the year, or which is operational in the year 2030 for the progeny device, for example, then we should maybe not build it in, for example, Germany. Maybe only some regions would be under the threshold we were choosing. But yeah, maybe we think about France or Spain. So that's possible with this impact screening method. Then we were also asking ourselves the question, does the location matter? And is there maybe a trade-off? When does the location matter? And here you can see for ISO standard 5, the indicator map for the year 2030, and for ISO 9, and also for ISO 5, it looks more like the region map for the energy mixes. But for ISO 9, it looks more like the temperature map. So there must be a certain kind of trade-off between the parameters we chose. So for that, we took a look at the correlation matrix of the different parameters, and we could already see that the energy demand correlates with the impact of electricity from the different regional mixes. This is the same result, just a bit more visual. So there is sort of a trade-off in the correlation map. So this is a different way to show it. So we had parameter 1. Parameter 1 is the energy which is needed to maintain a certain ISO standard. And parameter 4 is the parameter which is the energy demand which is needed for heating and cooling. So it's more the regional parameter. And the other one is more an operational parameter to have a certain cleanliness level. And we can say that for ISO standards, which are higher than 6, the location does matter. But if it's a lower number, so a higher cleanliness of the room, then it doesn't matter where it's built, because the impact will only be the energy mix. But if it's the ISO standard higher than 6, then we should consider also the location. So this is the end of the presentation, and we could show within the progeny project that it's possible to use the scenario methodology with a little bit of a twist, turn it around and use it as an impact screening method, allowing like all the solutions, skipping the cross consistency check, which is also not possible in this solution space, because we want to allow all the solutions. We want to have this, multi-purpose or multifunctional background data for the clean room usage. So lifecycle assessment analysts can now use this data. They can now say, okay, I want to build a clean room in the year 2050, and it has to have the ISO standard 5 or 4, and then they can directly access the data and use it in their lifecycle assessment. Okay, then thanks for your attention. And if you have any questions in regards of this research, we are happy to answer. And I'm sorry that we already are past the time.
Yeah, thanks a lot, Flora. Maybe we can take 2 minutes if there's any participant that wants to ask a question. Thanks for joining us again, and thanks Flora and Bernard for the great content. Anyone that has a question, last burning question? Yeah, thank you for joining, Stanislava. And I'm sure there will be, with many of you participants today and all those and other people that will watch this video online, there will be possibility for future exchanges as well. All right, then we close this session now. Thanks a lot for joining again, and you have a good rest of the day.
Yeah, thanks. Bye.